Hi everyone, welcome to this series on ancient Greek science. My name's Claire Hall. I'm an exam fellow at All Souls and I work on stuff both to do with prophecy and divination and various topics in ancient science. I've been giving these lectures for 3 years now, but this is the first time they've been online. When I was an undergrad, I went to an annual series of 72 lectures on maths and science, from Parmenides to Bertrand Russell. These lectures were for an audience of mathematicians, without any particular background in history, so we spent a lot of time going over contextual information, sometimes through elaborate caricatures, about Greek, medieval Islamic, medieval European, and European Renaissance culture. I'm not going to be doing that in this series of lectures. What I will be trying to do in these lectures is to pick a few points of interest in the general umbrella of texts, thinkers, and subjects that come under the term ancient Greek science, and discuss them in some more depth. I will sometimes discuss some background historical context, and very occasionally I do refer to later science, but mostly I'm going to keep quite focused on the thinkers and topics at hand. In this first lecture, I'm going to be talking about history of science as a subject, why do it, how you can do it, and what it means to talk about science in the ancient context. The rest of the lectures will then be on specific topics in ancient science. Lecture 2 will be on epistemology, which is arguably a topic in ancient philosophy as well, so some of you will be familiar with it. But that will look at what does it mean to know something, and particularly what did ancient scientific thinkers count as knowledge. This will include some bits on logic as well. Then in the third lecture, I'm going to talk about cosmogony and cosmology. That means accounts for both the creation and the current structure of the universe. Lecture 4 will move on to astronomy and astrology, i.e. how the study of the stars and planets worked in Greek science. From then, in week 5, I'll go on to biology, and that will include some stuff on botany and zoology. In the 6th lecture, I'll talk about medicine. Lecture 7 will deal with maths. Mostly it'll be on geometry, so what we think of as pure maths, but I will talk a bit also about some applied topics like harmonics, that's musical theory, and optics as well. And then in the last week, lecture 8 will be on engineering and technology. That'll be more of a survey of various cool things from ancient engineering and technology. That's probably the most fun of the lectures, and I think we'll all need it by week 8. Before I dive into the first lecture today, I'm going to give you a quick outline of how this course is going to work. So as I just said, there's a total of 8 lectures in this course. At the moment, I've uploaded the first 2 lectures onto Panopto, and then the rest will follow over the next few weeks. Apologies if you're very familiar with all this stuff and have been going to lectures online the whole time. This is my first time doing it, so sorry if I am over-explaining here. The lectures don't strictly need to be watched in order, but sometimes I will refer to things that I've said in previous lectures in later ones, so it does make most sense to watch them in the order that they're labelled. This course doesn't have tutorials. As you know, if you're here, it's not examined, it's for fun and general interest, so I'm not going to assume much background knowledge, and I'm not going to be setting loads of reading. I will put some bibliographical stuff up in case you do want to follow things up. Different people will find different bits of this course pitched too easy or too difficult. Depends a lot on the background you've got in science, but also in ancient philosophy. It's, of course, totally fine to skip ahead in the video and watch bits you want. I won't know. I won't be offended. Each lecture is going to be about 50 minutes long. I've broken it up into sections. There'll be some images, maybe. I encourage you to pause it when you want, have a break halfway through, get a glass of water, whatever. It's boring enough trying to keep focus in a normal lecture, let alone online. I've tried to divide it up in a way that will make that easy for you to do. If there's demand for it, I'd be happy to do some live Q&A sessions on Microsoft Teams. What I suggest for that is that when we get to midway through the course, if you would like some Q&A sessions, get directly in touch with me. I'll put my email address on the screen now. If people do get in touch, I'll pick a time and schedule a few sessions. They can be informal, just a chance to go over some of the material, talk about any questions you have, discuss what you might read next if you'd like to follow something up. The reason I'd like to leave it to halfway through term is that I assume that you have a lot of these kinds of things, live team sessions. I do too. I don't want people to feel like it's just another thing they have to go to. But if you would like to talk about any of the topics, I'm more than happy to, so please don't hesitate to get in touch. Okay, let's get on with lecture 1. So, history of science, and the history of science. History of science has been quite a patchy subject. Academic histories of science started to be written in the West in about the 1830s. One of the first and most famous from that period is by the polymath William Whewell, who was based in Cambridge. Whewell himself traces the origins of the history of science to Francis Bacon at the turn of the 17th century, Bacon being a very influential empiricist and particularly involved in the development of the scientific method, so that's probably why Whewell picks him for that. Most of these early histories of science, including Whewell's, have quite a similar structure. They tend to start with the Greeks, they spend some time on that. They maybe mention a bit of stuff from the Islamic world and the medieval Islamic world and the medieval European world, but most of the work comes when they talk about the Renaissance and the scientific revolution. For many of us, that structure is actually quite familiar. It's roughly how the mental picture of intellectual history still feels. That is, those of us who don't have any training in non-Eurocentric history or haven't specialised in medieval history or anything like that. So sure, we know some stuff happened in other places in the world, and we know that the Middle Ages surely weren't as boring as they seem in many of these accounts. But for most of us, it's still quite natural to think of science as only really getting going in the 18th and 19th centuries. There's something in that. It's obviously not completely wrong, and science as we think of it now does have many elements that became norms at that point. But I want to show you a bit today about how limited a view that is. Particularly, I want to talk about how it can give us a wrong sense of what Greek science is about. So after Whewell, after the 19th century, it was only in about the 1920s that history of science lecture courses first started being taught in universities, first in the USA and then across the Western world generally. One of the most famous of these was by Thomas Kuhn at Harvard in the late 40s and 50s. Kuhn is most famous for his book, The Structure of Scientific Revolution, which argued that scientific cultures undergo what he called paradigm shifts. Now, a paradigm shift works something like this. So everyone in a particular scientific field agrees on some basic assumptions, like, say, for example, the Earth is at the centre of the universe. There's 7 planets. The orbits of the planets are circular. People spend their time working on making accurate observations, making mathematical models that then fit those observations and explain all the phenomena, and then arguing about the implications that science has for other types of knowledge. There may be some metaphysical speculation, some professional disagreements, but everyone's working roughly within the same set of assumptions and norms, even if they disagree on details or where future work should be going. Then what happens is somebody proposes a model that's radically different. For example, in this case, someone proposes that actually maybe the orbits aren't circular, they're elliptical instead. Or maybe the Earth isn't at the centre, the Sun's at the centre. What happens? Well, sometimes somebody proposes that and nothing happens. Nobody pays any attention. The paradigm continues. But sometimes these theories begin to catch on, and people realise the uncomfortable truth that the new theory just fits the facts, fits the phenomena better than anything else. And so the whole community, in dribs and drabs, agrees to throw away some of the starting assumptions and adopt new ones. You'll see from the way I talked about it, the clearest example is the so-called Copernican revolution, when people switched slowly and gradually from a geocentric model to a heliocentric model of astronomy. We'll come back to that in week 3. In general, most historians of science these days are on board with some notion of paradigm shifts, something like that. Still the most common way of talking about different scientific cultures through time and in different places. However, the term should be used with some caution. it's not as simple as claiming that different geographical and temporal cultures had just completely different paradigms with no commensurability. It's not like you throw everything away and everything's completely new. There clearly are elements of continuity, and there are also clearly better and worse explanations of physical phenomena. But it does a good job of reminding us to look for what the kind of central grounding observations and assumptions are, and not to think of previous science as preparatory study for modern science. Throughout these lectures, one message I'd really like you to take away is that it is very tempting to say things like, oh wow, Anaximander's cosmology, it kind of anticipates Newton. Or something like, Epicurean physics, it's kind of like a very basic version of quantum theory. Or other things like that. Saying things like that is very tempting, but it can get you into a mode of thinking about science of the past that's very unhelpful. You may be familiar with some of these criticisms from other study you've done of ancient history, that historians often talk about not imposing modern categories on the past and so on. You may also think, well, yes, sometimes it's just helpful to do that, to think of the Delian League as NATO or whatever comparison you happen to have in mind. Both of these things are true in my experience, but it's even more acute in the history of science than in other types of history, that it's very important to be really clear on when you're making modern assumptions and comparisons, just, because it's helpful to just get a basic grip on something, and when that's actually starting to make you think about topics in the past in a way that is so anachronistic that it's actually stopping you understanding them properly. Science is more than other fields, I think, into the idea of progress, and it's very easy to slip from an idea of progress into a picture of a linear development of science through different periods. Two terms you may have heard that resonate with this idea are teleological history and Whig history. Teleology is a bit more straightforward for those of us with a background in Greek. It comes from telos, which of course is used most influentially by Aristotle as a technical term in his theory of causation to talk about what he calls final causes, the reason why something is the way it is. For example, the final cause of a boat is sailing. We'll come back to that, the theory of causation. I'm afraid it will crop up a lot. The notion of teleology in terms of history is the idea that things are organised leading up to a point, and that point is now. Whig history is a related term coined in the 30s by Herbert Butterfield, a historian of science, to criticise that tendency. Butterfield's use of the term is both about scientific histories, so ideas of the kind of onward march of progress, but he's also talking about political history. Butterfield is critiquing the idea that with the progress of science comes the inevitable development of European-style constitutional government, individual freedoms, that kind of thing. So a type of history that sees the scientific revolution and the Enlightenment in Europe as ongoing, part of the same project, as a kind of development of civilization, with the implication that all cultures will inevitably develop in that direction. Whig history has helpfully, since Butterfield, come to take on various additional connotations about the centering of Europe, and I guess later on the US, in this story. Many historians of science, both those from non-Western countries, e.g. Didi Kosambi in India, Wu Wenjun in China, and many others, and increasingly also those from the West, have been pointing out that any overview picture of the history of science that focuses only on the West is an absurdly partial and Whiggish picture. Modern science is an enormous mishmash in terms of its origins. It contains a great deal of Greco-Roman stuff, sure, but it also includes a lot of Persian, Babylonian, Egyptian, North African, Indian, East Asian, and more than anything, medieval Islamic ideas and influences. While histories even as early as William Whewell's in the 1830s were aware of the Islamic influence on science, they tend to vastly underestimate it. Modern science, as we know, contains foundational ideas from a variety of different time periods, peoples, cultures, languages, through a series of surprising and often really scarily accidental and contingent confluences. So what's the relevance of this for us in terms of teleological and Eurocentric historiographies? Well, I think this. If you have a particularly teleological or Eurocentric view of the history of science, then I think that means that Greek science can often take on a bit of a distorted place in your picture. We get this notion, if we have those teleological and Eurocentric pictures, that Greek science is kind of the direct linear ancestor of modern science, and that the development from Greek science to modern science is a kind of linear, necessary, or at least inevitable European story. This historiography has the consequence of producing an unhelpful notion that Greek science is basically quite familiar. It's a kind of prototype, a preparatory study for modern science, and therefore that its starting assumptions, its scope, its motivations and aims are, a bit different, but basically the same as those of our own scientific culture. And I hope that those of you with a background in classics will be used to now thinking about how fundamentally weird and alien loads of aspects of Greek culture are. I want you to apply this to Greek science. One of the themes of this lecture course is not to focus on which ways Greek science is like modern science, but kind of the ways in which it's its own thing, with a different set of norms and a different relationship to philosophy, religion, and society, to modern science's relationship to those categories. Indeed, one of the things I'd like to convey is that although we use the term science about the Greek world, and I'm using that term here, there's a case to be made that it's got such serious overlap with philosophy and religion and all these other categories that do they wholly make sense, that maybe we shouldn't even be using that term. We'll get back to that. For now, let's look at a specific example. So an example of how Greek science can take on a distorted place in a teleological or a Whiggish history. So there's this quite common conception, particularly in histories of the early, mid-20th century, but to be honest, it continues throughout and sometimes still gets used, is the conception of Greece as the birthplace of science. Mostly this kind of terminology is not used anymore in academic histories of science, but it does still sometimes appear, and it's certainly there in popular histories of science. This is sometimes known as the Greek miracle, a term I find spectacularly unhelpful, or slightly less unhelpful, the Greek awakening. So those terms both usually they can be used to refer to a couple of different things. Usually they refer to a period in the 6th century BC, said to start with Thales of Miletus in Western Anatolia, where Greek scientific thought kind of sprang into existence. It's used very widely in that way. Sometimes it just means that the start of what gets called scientific discourse. Sometimes people use the same term, the Greek miracle or the Greek awakening, to mean something far more specific, which is the axiomatic deductive method of mathematical proof, as it appears in Euclid. We'll come back to that use of the term. That's a bit too specific and complicated to talk about now. But most people, when they do use this term, mean the first thing, i.e. scientific ways of talking and thinking just kind of appear in the 6th century. What do we think of this? Well, there's two features of the Greek miracle that Geoffrey Lloyd thinks are the things that people are paying attention to. Geoffrey Lloyd wrote a couple of sort of textbooks of ancient science in the 70s. They've been updated since. I still think they're the best introductory books to Greek science. I will put a picture of them up on the screen. These are very good if you'd like to just kind of read something that covers many of these topics but isn't too heavy. And he has a very, very good examination of what people are talking about when they talk about the Greek miracle. So he says there's these two features that people are actually really pointing at. The first of those is an absence of supernatural elements in explanations for physical phenomena. The second one is a culture of discourse and criticism where participants propose models, and those models are either accepted by other people, or they're tweaked a bit and then accepted, or they're just rejected. No, that's not a good explanation. And he says that what people are getting at when they're pointing to that is there's a lack of mixing. It's not that you can just accept multiple different explanations for the same phenomena. You must decide on the best explanation. Lloyd gives an example of earthquakes. He explains that Anaximander, an early thinker who we'll return to in the next lecture, explains earthquakes as the result of turbulence in the water sphere beneath the Earth, an explanation which is coherent with his cosmology. Now, initially, that might sound slightly silly to you. Water sphere, what's going on? But actually, think right now about what you know about the core of the Earth. I at least picture it as a sphere of fire. Earthquakes happen in a really basic sense. Why? Because tectonic plates are moved around on the sphere of fire that hit each other. So it's not that different in a very basic way. The important feature here is that Anaximander doesn't say earthquakes are because Poseidon shakes the earth, which is what would count as a supernatural explanation in the way people talk about the Greek miracle. As you know, that is an explanation that is regularly used in Greek thought. It frequently crops up in the Iliad and the Odyssey and other places. Poseidon, the earth shaker, caused an earthquake. The other feature, the lack of syncretic mixing, is that Anaximander isn't saying earthquakes happen because there's movement in the water sphere and Poseidon shakes the earth, or okay, yeah, it's both of those things. He's saying no, there's a physical explanation for these phenomena, and so what people are trying to point at is that somehow this way of talking scientifically has just appeared. I think we've got to be careful. This doesn't mean that the pre-Socratic scientists, so-called, didn't believe or consider the gods important. It's, I think, more that they had a less interventionist picture of the gods than traditional religion, which meant that while the gods may have set the world up to be the way it was, they're not interested in regulating its everyday natural phenomena. The other feature, the thing about discourse, is explained by Lloyd as being part of a much wider picture of political activity and engagement in ancient Greece in this period. This is an argument I find very convincing. So Lloyd argues the city-states of archaic Greece have a vast variety of different modes of governance. The early democracy of Athens, the Ephyra in Sparta, a kind of diarchy. Political discourse is a huge feature of Greek dialogue, both within and between states in this period, and the political cultures of Greece, particularly of Athens, valorised a kind of competitive and argumentative engagement that made the idea of competing scientific discourse feel probably extremely natural. Now, this idea of the Greek miracle has become less popular and more nuanced in histories of science through the 20th and into the 21st century, as I mentioned. Geoffrey Lloyd himself, he uses the term with some scepticism in his books in the 70s, but he now kind of has said just basically don't use this term. It is still quite often there, even if the term's not there as an underlying concept in history of science. And I think, again, it's one of those things where there's a kernel of truth in it. These are the first times in Thales and the Milesians that we see these kind of explanations for physical phenomena with a lack of supernatural elements and with a kind of like, no, you're wrong, it's not this, it's actually this. But I think we should be really careful about thinking of it as the start of science. The idea that science is a kind of clearly definable thing that started to happen. I guess before we get further into the content of and further examples of Greek pre-Socratic thought, it might be good just to say a little bit about the definition of science. Now, I've touched on this, but let's go into it a bit more. So, in much of the literature on ancient science, there's a discussion of whether it's appropriate to speak of Greek science. And as I mentioned before, some people completely just get rid of these terms. In later contexts, in the medieval or early modern world, a lot of scholars go for a different term. They go for the term natural philosophy, which I think is an all right solution, but often it's just calling the same thing by a different name. I personally am of the camp that says that we don't need to have a super precise definition for the term science to be able to use it meaningfully. And I'm sure when you clicked on the link on the lecture series that said Greek science, you had some idea of what you were getting yourself into. If we turn to what the term means in the modern context, it's actually not as straightforward as we sometimes would like to pretend. David Lindberg, who's a historian of ancient and medieval science, says that there's at least 3 different camps of modern definitions of science. So the first one is that sometimes when people talk about science, The thing that they think makes it science is that it's an organised, systematic knowledge of the material world. Okay. Sometimes, the second definition he proposes, sometimes when people talk about what makes science science, they're talking about a way of knowing whose methodology is the experimental scientific method. So that's to say that sometimes people define science, they say it's science because it uses the scientific method, and anything that uses the scientific method is science, and anything that doesn't isn't. The third kind of definition is a much more kind of functionalist one, and that just says science is the collected current teachings of physics, chemistry, biology, geology, psychology, etc. i.e., it's a body of knowledge. It's the sum total of all the things we think of as the sciences. Now, Lindbergh says all of these definitions crop up quite regularly, and he thinks that we shouldn't be trying to get more specific than this. Modern science kind of fits best with a mixture of these definitions. Now, he says when we take this to ancient science, we should be focusing more on the first and third definitions, he says, i.e. what the objects of science generally are, how it's organised, and then its separate disciplines, organised knowledge of the material world and the sum total of these different disciplines. He thinks the scientific method is not really relevant. And I think that's right. There is a bit of a tendency sometimes in history of science to get quite hung up on the scientific method as the barometer for what counts as scientific thinking. Okay, what I want to do now in the second half of this lecture is to give you an idea, an overview of sorts, of the kinds of people, places, and ideas we're going to be dealing with in this lecture course. I'm going to do a run-through of some of the major people and groups in ancient Greek science. It will be a bit of a whistle-stop tour, so bear with me. Greek science tends to get separated into three quite sensible periods, sometimes four, depending on how late you go. These are the pre-Socratic period, the classical period, the Hellenistic period, and the Roman period. This should be a periodization familiar from ancient history generally. I don't always use these terms. Some people in ancient philosophy use the term post-Hellenistic instead of Roman because they're mostly talking about culturally Greek writers and don't want to be confusing. As with all things, the terminology is not totally consistent. Unsurprisingly, I'll begin with the pre-Socratics. So the first group I want to talk about are the Milesians, Thales, who we met earlier, Anaximander and Anaximenes. They were active from about the 550s BC to the 530s. We have no surviving texts from the Milesians, so it can be quite difficult to get a grip on what exactly their claims and doctrines are. We have to rely on testimony from later thinkers. There's a lot in Aristotle. But insofar as those testimony are reliable, we can build up a fairly good picture of what the Milesians' interests were. They were interested primarily in cosmology, cosmogony, and physics. These thinkers are known for proposing various models of the composition of the universe and consequent explanations for its physical makeup and processes. We'll return to this in the next couple of weeks, but for now it's worth noting that a striking feature of Milesian physics is the various claims made by different thinkers for a kind of primary underlying substance. So they mean primary both in terms of time, the first substance, and materially, the kind of underlying substrate from which other things are made. Their suggestions include, variously, air, fire, and the timeless. We'll get back to what that means, but it's a noticeable feature of Milesian physics. A little later after them, you get the emergence of the Pythagoreans in about the 520s BC, 510s. My former teacher, Piers Bursell-Hall in Cambridge, has an extended argument that Pythagoras as a person never actually existed. Maybe true. I won't get into that here. It's true that our biographical information for him is extremely shaky. Nevertheless, whether he existed or not, there was clearly a group of people who called themselves the Pythagoreans. They had some of the same concerns as the Milesians, some cosmology and so on, but their focus was a bit different. Their general approach is more comparable to other kind of contemporary religious or mystery cults, such as Orphism, which shares with the Pythagoreans a strong focus on theories of reincarnation and metempsychosis. that is, the transmigration of souls from one body to another. And when I talk about them a bit more, you'll see what I was saying earlier on about how the lines between science and religion are a bit shaky here. What's unusual about the Pythagoreans was their attitude to number. They were particularly interested in the properties of numbers. Whether we should think of this, if we want to think of it in modern terms at all, as kind of number theory or something a bit more like numerology is less clear. They did, of course, also take an interest in geometry, as in the famous Pythagoras' theorem. Their interest in geometry also included a great deal of study of music and harmonics. After them, over the period of 520 to 460 or so, you get several more distinct figures who are important in pre-Socratic philosophy, including Xenophanes, Heraclitus, Anaxagoras, and Empedocles. I won't spend much time on these guys, although I will talk a bit more about Empedocles and his cosmology in week 3. It's worth noting that Empedocles is generally thought to be the first person to espouse a physics of the classic 4 elements, that is, earth, air, fire, and water, and this becomes very popular. There's a group I want to mention as well in the same kind of period, in the 480s down to the 440s or so, and they're the Eleatic skeptics. They're referred to that way because they come from Elea, but also to distinguish them from the later related philosophical school of skepticism. So the Eleatic skeptics, the two most famous of them are Parmenides and Zeno. I'm sure you're all familiar with Zeno, with his paradoxes, for example, the one about the race between Achilles and the tortoise, and I will be talking about that a bit. The defining feature of the Eleatic skeptics and their skepticism is their questioning of the basic tenets of previous descriptions of physical phenomena. I'll come back to them in more detail, but it's important to note that many of the questions they asked, such as what does it mean for something to change, or what does it mean for something to be infinite or continuous or discrete, and so on, had a huge effect on the epistemology of thinkers following them, and I will talk a bit about them next week. I'm also going to mention the doctors, especially Hippocrates and his circle. So Hippocrates of Cos, who gives his name to the Hippocratic corpus, was doctor in around the 440s BC. He trained at the Asclepion, sanctuary of Asclepius, in Epidaurus in the Peloponnese, and that I'll come back a bit to the Asclepia, and again this strange boundary between religion and science. Boundary is maybe a wrong word. The Hippocratic corpus is the name given to a large collection of medical texts which come mostly from the school of Hippocrates, but also from a rival medical school which was in Cnidus. Some of the texts in the Hippocratic corpus probably were by Hippocrates himself, but the vast majority of them are by anonymous authors. We're not even certain that all the authors were medical doctors. The earliest texts in the corpus date from around 440 BC, with many of them written over the rest of the 400s and 300s. There's a bit of dispute about how late they go. They treat a whole range of topics in medicine and biology, including pathology, diagnosis and prognosis, treatment, surgery, medical ethics, physiology, embryology, and gynecology. I'll be discussing this corpus, Hippocrates, and particularly the more religious elements of medical practice in some detail in lecture 6. There's one more pre-Socratic group I want to mention, and that's the early atomists, Leucippus of Miletus, again Miletus, and Democritus of Abdera. So they come up with a physical theory of atomism, which of course has a long life in Greek and indeed in modern thought. As with Pythagoras, there's some confusion as to whether Leucippus was actually a real person or was a sort of quasi-mythical figure associated with Miletus, perhaps attached to that place because of its associations with Thales. In any case, unlike the Eleatic skeptics, the atomists had the notion that matter's not continuous and infinite, but is instead broken up into dispersed atoms which are scattered around in void. There's a tradition that Democritus, who developed and enlarged this theory, was friends with Hippocrates the doctor, which would be interesting if true. We'll return a bit more to atomism in the next lecture. Okay, so that's the pre-Socratics, and you can see there's a whole range of different things they're doing. Now we've got to Plato. You'll all know something about Plato. I suspect some of you will know more than others. It's fine. Plato's interests, as reflected in the relatively large number of works he wrote, were very broad. I won't be focusing on his political theory, as found in the Republic and elsewhere, or on primarily ethical works like the Euthyphro and the Phaedrus, although it is worth noting that rhetoric and logic are both systems of Greek thought that have a reasonable claim to fall under the remit of science. I will talk about logic a little bit. The most important works of Plato for our purposes are the Theaetetus, the Meno, and most of all the Timaeus. Timaeus is often regarded as the most complex of Plato's dialogue. It's certainly the weirdest for modern audiences, and also it was regarded as pretty weird and complex in the ancient Greek educational curriculum. It was usually reserved for the late stages of a pupil's education, after that pupil was familiar with the rest of Platonic philosophy, basic rhetoric, logic, and geometry. The Timaeus presents Plato's cosmology and cosmogony, and an awful lot of really weird numerology. We'll come back to it in a lot more detail. For now, it's enough to mention the importance of Plato's theory of the forms, which is explored in several of his dialogues, and how it forms the basis of his scientific epistemology. So again, I will talk about this next week. But the theory of forms has at its centre the notion that human beings have the inborn ability to recognise divine archetypes of intelligible things, and in doing so, they can mentally navigate the physical, sensible world. That's to say, I'll come back to that later. Our other biggest figure from antiquity is, of course, Aristotle, who was born in Stagira in 384 BC, but lived most of his life in Athens, studying at Plato's academy and setting up his own school, the Lyceum. Aristotle's interests were perhaps even broader than Plato's and range, as I'm sure you know, through metaphysics, physics, logic, rhetoric, aesthetics, music, ethics, biology, cosmology, and astronomy. I'm not going to try and summarise him here, but from a historiographical point of view, it's worth noting that he's one of the most difficult people to understand as a whole, because he had such an unrivalled status in the history of medieval and later interpretation. So Aristotle, for both the Islamic scientists and the European scholastics in the Middle Ages, was the kind of the philosopher par excellence. He's often just referred to as the philosopher, or sometimes, for example, in Thomas Aquinas, he just says, he says this, and he means Aristotle. Islamic science tended to focus on Aristotle's physiological and biological work, but it was his understanding of logic that had the biggest influence in the medieval West. The reason this makes things complicated is it's very often the case with Aristotle that you think you know what Aristotle says about something, and then you go and read Aristotle and he says something actually quite different from what you thought. So I will end up talking about Aristotle most weeks. He's a bit unavoidable in that sense. So into the period after Aristotle, the centre of intellectual gravity of the Mediterranean world begins to shift. And as you can see from the map that I'm putting up right now, in the earliest period, the focus is in Western Anatolia, in the Aegean. In Miletus, in particular, we had Thales, Anaximander, and Anaximenes. The focus then shifts towards Athens in the late 5th and 4th centuries, Plato's Academy and Aristotle's Lyceum becoming particular centres there. But then after the time of Alexander the Great, a new centre of learning emerges in one of his new foundations, that's Alexandria in Egypt. And Alexandria remains the intellectual hub of the Mediterranean world from the Hellenistic period all the way through the Roman period, all the way through to the 5th century AD. It's rivaled only by Rome, and even then much scientific work is being done in Alexandria kind of rather than Rome. One of the most famous, so now we're into the Hellenistic period, so one of the most famous Alexandrians is Ptolemy, who may have been descended from the ruling dynasty to which Cleopatra belonged. As you'll know, Ptolemy's focus was on astronomical modelling. He seriously refined the earlier astronomical models of Eudoxus, who I will talk about. Ptolemy's Almagest, which is named after its Arabic manuscript recension, it's called the Syntaxis in Greek, but basically no one calls it that. It became the Bible of astronomy for well over 1,000 years. But his other important contribution was in one of his other important contributions was in astrology, with his theoretical handbook, the Tetrabiblos, which argued for a highly mathematised astrology based on the results and models in the Almagest. And I will be coming back to Ptolemy, and particularly to this issue of the relationship between astronomy and astrology in week 4. We also have from this period Epicurus and his Roman follower and translator Lucretius, and they represent a later generation of atomists. They follow in the tradition of Leucippus and Democritus. So they significantly refined atomic physics, ethics, and optics, and they included the addition of a number of metaphysical kind of extra bits. One of the most famous of these extra bits is the notion of the swerve, which you may have heard of, which is a kind of atomic random motion which preserves the notion of a non-deterministic human freedom. I'll come back to that, and I'll come back to Epicurus and Lucretius, particularly next week, and to the question of where physics and philosophy overlap in Greek thought. There's also two mathematicians from this period, the Hellenistic period, that I want to mention, Archimedes and Euclid. Archimedes we know quite a lot about. He was based at Syracuse in Sicily, and we know that he died in 212 BC in the Roman siege of Syracuse in the Second Punic War. Archimedes' inventions include the Archimedes screw, which is a thing for getting water up, various complex pulleys, a range of really quite terrifying war machines, which were very well known in antiquity. And I'll come back to some of those in the final week. His mathematics, particularly his mechanics, including his formulation of the law of the lever, wasn't so well known. It's only really in the Italian Renaissance in the 15th century that people get seriously interested in Archimedes in the Western world. In a longer course, I could tell you a lot more about this. He's he plays a very interesting role in the Renaissance. Anyway, Euclid we know far less about. We don't even really know where he was based. We don't know where he lived. We don't know where he was born, when he was born, any of that. We just know that he wrote the peculiar text we know as the Elements, which took mathematics and attempted to derive as much of it as possible from solid axiomatic foundations. I can talk a bit more about that next week, about what that means, why somebody might have wanted to axiomatize mathematics, which is quite an unintuitive thing to do. Okay, so the other person I want to mention from the Hellenistic period is Galen, or I guess he's into the Roman period. Galen will feature in Lecture 6. He was the most prolific medical writer of antiquity. Indeed, he was the most prolific writer of antiquity, full stop. His writings represent, this is mad, okay? His writings represent over half of all the ancient Greek texts we have. Much Galen is still actually unedited. Galen wrote on every topic represented in the earlier Hippocratic corpus and on many that are not. A feature of Galen's work, which is sort of generally Aristotelian Stoic in outlook, some Platonic bits, is that he performed a number of dissections and other more complex experiments, writing the results up with a clear structure of hypothesis, experiment, conclusion that we would recognise as broadly pertaining to the scientific method, although without such a strict criterion of repeatability. This is just one thing to pick out of Galen. Obviously, there's tons of things I could pick out, but I'm picking that out because it's interesting for thinking about science and the definitions of science that we came back to. There's some question marks to be put around these experiments, and I'll come back to them in week 6, but they're an interesting case study. Galen's works, like Ptolemy's, had a very high status, both in the Islamic and European medieval medical traditions. Many of Galen's texts remained the kind of standard medical texts until Vesalius in the mid-16th century, so he really did last a long time. So these are the main thinkers I'm going to be talking about. I know that's been quite a few of them, and it's been a bit of a whistle-stop tour. There have been several figures I have had to lead out, including some of the engineers who I might get to talk about in week 8. I've also not really talked about Latin scientific writers, Roman scientific writers, including Pliny, Varro, and Cicero. I will be mentioning them, a few Latin texts. I did mention Lucretius. Primarily the focus of this course is on Greek science, basically because there's so little Roman science compared to Greek science, and because so much of Roman science is, in its aims, very similar to Greek science. But I will mention a few Roman authors. So I hope this has given you a bit of a picture of what's included under the label Greek science. If we go back to Lindbergh's definitions, which I mentioned earlier, the 3 definitions or 3 types of definition of science, I think it should be kind of emerging by this point that, as I said earlier, that it's probably best not to focus too much on methodology, but more the first and third definitions, i.e., that science is a systematic and organised knowing of the material world, and that science is the sum total of the various distinct and recognisable types of study, including in the Greek context astronomy, biology, medicine, physics, geometry, harmony, optics, meteorology, many more. So I'll end with some definitions from Aristotle, which bring this out even more clearly. So in Book Gamma of the Metaphysics, Aristotle gives some definitions of what makes something a single science as opposed to kind of two or more different subjects. So he distinguishes two different ways something can be a single science, and he uses these two prepositional terms. He says something can be a science. It can be pros hen or it can be kath hen. So it's been argued that what this means is the following: something that's kath hen, it implies there's a unity of subject matter through synonymy. So, for example, horses and people are synonymously animals, so they're suitable candidates for being the object of one single science, that is, biology. Or, for example, geometry is the science of all the different shapes that are synonymously shapes, or botany is all the different plants which are synonymously plants. Pros-hen sciences, by contrast, imply a unity of subject matter by the relation of the objects of study to a single kind of organising principle or central theme. So the best example of this is medicine. Medicine isn't the study of a load of different objects that are all the same. It's the study of the principle of health. And so, yeah, these are just some approaches why, in Aristotle's mind, certain sciences make up a single science. But it's important to note that he's not claiming an overall category of science. There's one thing that is science. And I think it's this that's represented in Lindbergh's definition number 3, the idea that there's all these objects of study. If you add them together, that's what we're talking about when we talk about science. That's what I'd like you to bear in mind as we look in more detail at particular features of Greek science in the next few weeks.